Good morning, students. How are you? Yeah, in yesterday's class, we discussed two examples, worked examples, to determine the slope and deflections for a cantilever beam at free end by using double integration method, isn't it? Now, some more problems we will discuss in this class by using the same method, that is double integration method. When we use the double integration method, the double integration method is used to find the slope and deflections in the beam when a single load is applied on the beam. Okay. Let us go for the example 3. In this class, we will discuss example 3, that is a cantilever beam of span capital L carries a uniformly varying load of W per unit length at a fixed end. And 0 at the free end of the beam. What type of load it is? Uniformly varying load. The maximum load W at the fixed end and 0 at the free end. Find the maximum slope and deflections in the beam. Okay, students? Generally, at what point the maximum slope and deflections occurs in the cantilever beam? Cantilever beam, the maximum slope and deflections occurs at free end. At what? When whatever the load applied on the cantilever beam, either it is point load or UDL, whatever the load applied on the cantilever beam, there must be a maximum slope and deflection will be developed in the cantilever beam at free end. Okay, students, let us go for the solutions for this problem. Solution for this problem. The diagram shows that the cantilever beam means the beam which is fixed at one end A and free at another end B. The UVL is acting on that beam. The maximum load at fixed end W and 0 load at free end B. Okay. This is the UVL, uniformly varying load or triangular load. Let us consider a section XX at a distance of X from the fixed end. Okay, XX section at a distance of X from the fixed end. First of all, we have to find the bending moment at this XX section. After finding the bending moment, substitute that bending moment value in the curvature equation we derived in the previous classes. So after substitution in the curvature equation, by solving that curvature equation, we will get slope and deflection equations by substituting the boundary conditions. After that, we will get the final slope and deflections by eliminating the constants of integration. By using that slope and deflections, we can find slope and deflections at every point or at any point of the beam wherever we require. Okay, students? Okay, let us go in detail into this problem. So bending moment at XX is M. We are going to find the bending moment at this XX. What is bending moment? Bending moment at certain point is equal to the moments developed by all the forces on the right side of the section. The movement on the right side of the section clockwise is negative and anti-clockwise is taken as positive. Okay, students. Now we are going to consider a XX section. This is the XX section at which we are going to find the bending moment. So how to find the bending moment at this point? To find the bending moment, we should know the load acting on the right side of the section. What is the load acting on the right side of the section? So how to know the load on the triangular load? In this triangular load, we can find the total load acting on the right side of the section is the area of this triangle on the right side. So triangle area is of into length. The length, what the length it is from section to B? The section to A is X, total length is L. Therefore, the length from section to B is L minus X. Therefore, L minus X is the length of the triangle of into length into breadth. What is the breadth at base? How to find this breadth? How to find this height? We know the height at fixed end is W. So these are the similar triangles. Let us take the point C, A, B, C, and let us take this point as D, this point as E. So A, B, C and D, B, E are the similar triangles. So for these similar triangles, for smaller triangle, this DE, let us take that is Y, DE, let us take this height is Y. Y divided by height of the bigger triangle is W, that is the load, load intensity at A. That is equal to the length of the smaller triangle is L minus X divided by length of the bigger triangle is L. Okay, from this we can find the height of the smaller triangle DBE is Y equal to W into L minus X by L. W into L minus X by L. This is the height of the smaller triangle. I written here W into L minus X by L. So half into length into height of the smaller triangle is W into L minus X by L. L minus X by L. I written here, this is the load, isn't it? Load acting on the right side. This load will be concentrated. I shown here one arrow mark. This total load concentrated at certain point of the triangular load. What that point? Center of gravity. At center of gravity, the total load will be concentrated. That center of gravity will be located at a distance of length by 3 from the base. So what is the length of the triangle? TBE triangle L minus X. So at a distance of 1/3, that is L minus X by 3, it will be act. So from the section to load concentrate, the load which is acting at the center of gravity is L minus X by 3. So this is the load acting on the right side. This is the distance at which the load is acting from the section. Therefore, movement developed by this load at this section is load into perpendicular distance. So I written here 1 by 2 W into L minus X by L into L minus X. The of into W into L minus X by L into L minus X up to this load. And this is the perpendicular distance from the section. So L minus X by 3. So load into perpendicular distance is the moment. Here I am taking minus sign. Why I am taking the minus sign? The moment of this force about section is in clockwise direction. Therefore, we can take it as minus for the clockwise movement on the right side of the section. Okay, students? This is the equation for bending moment. So from this, m is equal to minus w by 3 into 2, 6l, l minus x into l minus x into l minus x, l minus x whole cube. So w into l minus x whole cube by 6l is the bending moment of the load about xx. Okay, students? So we know that curvature equation is ei d square y by dx square is equal to minus m. This equation is already derived in the last class, every first class of this unit 4. So curvature equation ei d square y by dx is equal to minus m. In place of minus m, we know that m value is minus w into l minus x whole cube by 6l. So by substituting m value here, minus minus plus w into l minus x whole cube by 6l is the ei d square by dx square is the curvature. Okay. So upon solving this equation, we can get the slope and deflection equation. A same procedure explained in the previous two problems. So solve this equation by integrating that above equation. Before integrating that equation, we should expand this L minus x whole cube. So W by 6L, that is A minus B whole cube form. So what is the formula for A minus B whole cube formula? L cube minus x cube minus 3L squared x plus 3LX squared. A minus B whole cube formula. A minus B whole cube is equal to A cube minus B cube minus 3A square B plus 3AB square. Okay. So like that I expanded here W by 6L, L cube minus x cube minus 3L square x plus 3LX square. Clear, students? Are you understanding these equations? These totally mathematical equations. We are expanding the L minus x whole cube and then integrate. By integrating the above equation, we get. How to integrate this? By integrating on both sides. On the left hand side, upon integration, we will get the ei into dy by dx. Upon integration of d square y by dx square with respect to x, we get dy by dx. Ei is the constant. As it is, we will write ei under dy by dx is equal to w by 6l into, what is the integration? What is the integration of L cube? L cube integration is L cube x. L cube is the constant and integration of constant is into x. L cube x minus x cube integration x power 4 by 4 minus 3L square x integration x square by 2, 3L square x square by 2 plus 3L into x square integration x cube by 3. 3 cancel, therefore we can get L x cube plus C1 is the integration constant. Okay, students? By integrating once again we get, again integrate this equation, we will get the EIY. This equation is slope equation, including the constant of integration. This is the deflection equation, including the constants of integration. So upon integration on both sides, we will get on the left hand side EI into y. dy by dx integration with respect to x is y. That is equal to w by 6l into L cube x integration L cube x square by 2 minus x power 5 by 20. So x power 5 by 5 is the integration of x power 4. 5 into 4 is 20. Minus L square x cube by 3. 3 by 2 into L square x cube by 3. 3 cancel. Therefore, we will get L square x cube by 2. Plus L x cube integration L x power 4 by 4. Plus C1x plus C2. So C1, C2 are the integration constants which can be determined by the following boundary conditions. These are the boundary conditions for the cantilever beam. These are the fixed boundary conditions. At x is equal to 0, dy by dx is equal to 0. Wherever the x 0, we should substitute the slope value is 0. Okay, students. slope value 0. So the fixed end at x is equal to 0 means at a fixed end of the beam, at fixed end the slope is 0. How it gets the slope is 0, how to get the boundary condition? So it is a cantilever beam. If any type of load is acting on this beam bends like this. Bend అవుతుంది ఈ beam. So ఇలా bend అవుతున్నప్పుడు the maximum deflection at the free end. This is the maximum. Vertical displacement is maximum at the free end. The vertical displacement decreases towards the fixed end. The vertical displacement at fixed end is 0. So vertical displacement is 0. Therefore, at the fixed end, the deflection is 0. Y 0. And also, the slope is also 0 at the fixed end. If we draw the tangent at this point, if we draw the tangent at the free end after deflection, we will get the tangent like this. The angle made by this tangent with initial position is called the slope. If we draw the tangent here, the tangent like this, slope is decreases. And if we draw the tangent at this place, the slope is decreases. Like that, if you draw the tangent at fixed end, it will be coincide with the horizontal position. Therefore, the slope at this point is also 0. The tangent which is horizontal, which makes an angle of 0 with initial position. Therefore, slope at fixed end is 0. Slope at deflection at fixed end is also 0. So these are the two boundary conditions for the cantilever beam we will take to find the constants of integrations. At a fixed end, the deflection is 0. At x is equal to 0, y kuda 0. These are the two boundary conditions. So from boundary condition 1, that is at x is equal to 0, dy by dx is equal to 0. Upon substitution of first boundary condition into our slope equation. So by substituting the x is equal to 0 in the slope equation, dy by dx is equal to 0. So x is 0 అయినప్పుడు these all the parameters are 0. So w by 6l into 0 is 0. And left hand side dy by dx is also 0. We should substitute. Therefore, c1 value is 0. So from the boundary condition 1, c1 is equal to 0. First integration constant will be eliminated. And by substitution of second boundary condition into deflection equation, y equation lo idi substitute cheyali, dy by dx equation lo first boundary condition substitute cheyali. So from the boundary condition 2, what is the boundary condition? Second boundary condition, by substituting the x value 0, the deflection is also 0. So left hand side y 0, therefore left hand side 0, right hand side in every parameter x is there. So up to this, the total parameters are 0. By substituting in place of x 0, we will get c2 value is 0. Okay, students. So upon substitution of both the boundary conditions, we will get the constant of integrations. By eliminating the constant of integrations, we will get the final slope equation and deflection equations. By substitution of c1, c2 values 0, we will get this final slope equation and deflection equations are these two. Final slope equation, I rewritten this equation without c1. Again I written this equation without c1 and c2. So ei dy by dx is equal to this equation, slope equation it is called, and final deflection equation without any constants. So c1, c2 are 0. If we get the c1, c2 values other than 0, we must substitute at this place. c1, c2 values substitute in slope and deflection equations. Then we will write the slope and deflection, final slope and deflection equations. Clear, students? Then maximum slope. In this problem, we are going to find the slope, maximum slope and deflections. Find the maximum slope and deflection. Where will we get the maximum slope and deflections for the cantilever beam? For the cantilever beam, maximum slope and deflections occurs at a free end. Just now I explained what is slope and deflection, maximum slope and deflections. Therefore, to find the maximum slope in the beam, we should substitute at x place L. In place of x, we should substitute L value in the slope equation. Then we will get the maximum slope. So upon substitution of L value in place of x in slope equation, this is the slope equation, ei dy by dx. We are going to find dy by dx, maximum dy by dx. So maximum dy by dx is also represented as maximum theta. So dy by dx is also represented as theta. So ei into theta maximum is equal to w by 6l. In place of x, we are going to find the l value. So l cube into l minus l power 4 by l. In place of x, we are substituting l value into this equation. So minus 3l square into l square by 2 plus l into l cube. So l power 4 minus l power 4 by 4 minus 3l power 4 by 2 plus 3l power 4 plus l power 4. So from this, w by 6l into 8 is the LCM for this all the parameters. 8l power 4 minus 2l power 4 minus 2l power 4 plus 8l power 4 is there upon 8 minus 8 plus 8, 16 minus 14, 2. 2l power 4 by 8. 2l power 4 8 by 8 means l power 4 by 4. So wl power 4 by 24 l. So WL cancel, one L is cancelled, WL cube by 24. We'll get the WL cube by 24 EI theta maximum. So theta maximum is WL cube by 24. EI is the formula for maximum slope at free end. Okay, WL cube by 24 EI. In this formula, W is the uniformly varying load. That is maximum load at fixed end. L is the span of the beam. E is the Young's modulus, I is the moment of inertia. Both EI is combinedly called flexural rigidity. It represents the strength of the section. Then maximum deflection. Maximum deflection is also occurs at the free end, that is at x is equal to L. By substitution of L value in place of x into this deflection equation. To find the deflection, maximum deflection, we should substitute L value in place of x in the deflection equation. So upon substitution of x value in place of x, L value, we will get the maximum deflection. So EI y max will write in the next step, EI into y maximum is equal to W by 6L, L cube. Here L cube is there, x square by 2. In place of x, L square by 2. So L cube L square by 2 means L power 5 by 2. Here I write L cube L square by 2 minus L power 5 by 20 minus L cube L square L cube by 2 plus L into L power 4 by 4. So from this 20 is the LCM. 20 is the LCM. Here 2 is there. 10 into L power 5 minus L power 5 minus L power 10 into L power 5 plus 5 into L power 5. It will be in the denominator 4 is there. 4 5 is 5 into L power 5. So 10 minus 10 is cancelled. 10 L power 5 minus 10 L power 5. 5 L power 5 minus 4 L power 5 is the 4 L power 5. 4 L power 5 divided by 20. So W by 6L into L power 5 by 5. W L power LL cancel. W L power 4 by 30. So Y max is equal to WL power 4 by 30. EI is the formula for maximum deflection at free end. Simply we are substituting the L value in place of X in the deflection equation. Then we will get the maximum deflection in the beam. Clear, students? Like this, you have to find the slope and deflections in double integration method, whatever the beam and loads are given in the problem. Okay? Procedure is same as that of the previous case. For every problem, the procedure is same. First of all, we have to take the XX section and then find the moment at XX section. And then by substituting that moment value in the curvature equation, after substitution, integrate twice that equation, we will get the two equations, including the constant of integrations, and the substitute the boundary conditions in the equations, then we can get the constant of integrations. After getting the constant of integrations, write the final slope and equations by eliminating the constants, and then find the slopes and deflections at every point, at each point of the beam, wherever the slope and deflections are asked in the problem. Okay, by substitution of X value. Then let us go for the second example, that is example 4 in this class. A cantilever beam of span, this is another case. if the moment is acting on the beam. A cantilever beam of span L subjected to a clockwise moment M. Clear, students? Clockwise moment M at the free end of the beam. Find the slope and deflections at the free end. Again, in this problem, in place of that a load is not acting, a moment is acting, clockwise movement at the free end. And we are going to find the slope and deflection at the free end. This is the given diagram. The diagram, you should draw the diagram yourself in the examination. Okay, the diagram is not given in the problem. You have to draw the cantilever beam and draw the locate the moment, clockwise moment M at free end, like that. Like here mentioned that. This is the moment. Okay, students. So what is the first step? We have to consider a x-axis section again. X-axis section at a distance of x from the fixed end. Always the section will be considered on the left end of the beam, left end of the beam. The positive x direction, in the positive x direction, the x increases. So bending moment at x-axis is, bending moment at this place is mx. We are taking mx in this problem because m is the clockwise movement. Clockwise movement is taken as negative, isn't it? Anti-clockwise movement is taken as positive. So here mx is the bending moment at x-axis is equal to minus m. Minus m is the couple or moment is acting at the free end. Minus sign for clockwise movement. So from the curvature equation, ei d square y by dx is equal to minus mx. In place of mx, we substitute minus m. Minus minus cancel, plus m, ei d square y by dx is equal to m itself. So upon integration of this equation, ei dy by dx is equal to m is the movement developed at that point. It is a constant integration mx, plus c1 is the constant integration constant. By integrating once again, ei equal to mx square by 2x, integration x square by 2, plus c1 is the constant c1x, plus c2 is the another integration constant. Clear, students? Then మనం 2 times integrate చేస్తున్నాం. ఒకసారి integrate చేస్తే left hand side d square y by dx square becomes dy by dx. Again we will integrate this dy by dx, we will get the y value. Okay, after our integration of dy by dx, we will get the y. If we differentiate y, we will get the dy by dx. If we differentiate dy by dx, we will get d square y by dx square, like that. Integrate చేస్తున్నాం ఇక్కడ. Integrate చేస్తున్నప్పుడు order will be decreases. D square first, d next, then y. So after getting the equations for slope and deflections, by eliminating the c1, c2, we can write the final slope and deflection equations. Again, substitute the boundary conditions to get the c1, c2. Upon substitution of these boundary conditions, we will get c1, c2 values 0. Always the cantilever beam, for the cantilever beam, constant of integrations are 0 for in a double integration method. Only in double integration method only, the c1, c2 values 0 for cantilever beam only, not the other beams. Okay. Therefore, slope equation is, what is the slope equation here? C1 is 0. If C1 0, ei dy by dx is equal to mx. What is the deflection equation? Ei y equal to mx square by 2. These two are 0. C1, C2 are 0. So ei dy by dx is equal to mx. Ei y equal to mx square by 2 are the equations to calculate the slope and deflections at each point of the beam. So here in this problem, the question is to find the slope and deflection at the free end. So at free end means x value is L value. Slope at the free end of the beam. First one, slope at the free end of the beam. At the free end, x is equal to L. So upon substitution of x plus L in place of x L, we will get the slope at free end. So ei dy by dx is replaced by theta. If you substitute in place of x L value, we can write the theta b. We are going to find the slope at the free end b. Ei theta b is equal to m into L. L is the x place, in place of x, substitute L value. So ml. Therefore, theta b is equal to ml by ei. This is the slope at free end by acting the moment m at free end. Okay, students, are you getting my point? A deflection at the free end. Again, we are going to substitute in place of x, L value in deflection equation. So EI, YB, whenever you substitute L value in place of x, we can write y as YB. That is the deflection at free end. EI, YB equal to m by 2 into L square. In place of x, we are substituting L value. Therefore, YB is equal to ml square by 2EI is the formula to calculate the deflection at free end of the beam when it is subjected to a clockwise movement at free end. Okay, students, this is an easy problem. Two formulas we have developed in this problem. Up to now, fourth example, total cantilever beams are solved. Now, fifth example is related to the simply supported beam problem. Simply supported beam. This, the blue color is the simply supported beam which is supported on both sides at A and B after deflection by applying the load. W is the load, point load at the center. The beam will be deflected like this. Beam will be deflected like this. After deflection, the beam position is like this. So after deflection, the slopes are maximum at fixed ends. Slopes are maximum. If you draw the tangent after deflection at B, the tangent is like this. And if you draw the tangent for deflected curve at A, we will get the tangent like this. So the angle made by the tangent with horizontal position or initial position is theta A, slope at point A. This is the clockwise slope. And the angle made by the tangent at B for the deflected curve, we will get the slope at point B, theta B, which is in anti-clockwise direction. It is -1. It is the anti-clockwise direction is negative slope. Clockwise slope is +1. And deflection is at this point. What is the deflection at the support after deflection? After bending the beam, the deflections are 0. The beam doesn't deflect. The beam is not deflecting at supports. Therefore, deflections are 0 at supports. And deflection is maximum at which place? At the center. That is the under the load, the vertical displacement of the beam is maximum. So displacement will be decreases towards the supports. Vertical displacement of the beam is decreases towards the support and 0 at the supports. Maximum deflection at the center. Okay. So if we draw the tangent at the center, it horizontal position. The tangent to the curve at the center, it will be given tangent is horizontal position. So tangent, whenever the horizontal tangent is horizontal, the angle made by the tangent is 0. Angle made by the tangent is 0. Therefore, slope at this center point is 0. Deflection is maximum, slope is 0. Wherever the deflection is maximum, the slope is always 0. Okay. So let us go. Let us read the problem first. Example 5. A simply supported beam of length L subjected to a point load of W, capital W, at its center. Find the slope and deflections at the supports and at the center. At every point, we have 3 points in this beam. A, B are the supports, C is the center point. Okay, we have to find the slopes and deflections at these 3 points. What is the slope at A, slope at B, slope at C? And similarly, deflection at A, deflection at B, and deflection at C. Okay, students, let us go for the problem. Let us solve this problem. So, first of all, you have to draw this diagram by reading the problem. So, a simply supported beam, you should draw the simply supported beam. Locate the L is the span and W is the capital W is the point load which is acting at the center. You have to mention the W at the midpoint of the beam. Okay, and take X-axis section. I cannot is called X-axis section. You should take the X-axis section in between A and C, from the left support. Okay, this section is only applicable only in between A and C. This section is not applicable between B and C. Okay, whenever this section will be crosses the C, this section is not applicable. It is invalid between B and C. Therefore, this double integration method is used for only single loads. This section is applicable. If you want to find the slope at B, you have to take another section between B and C. That's why this double integration method is updated to the Michaelis method. Michaelis method, wherever you take the section in between A and C or B and C, it will be applicable to at all the points of the beam. Okay, ఒకసారి మీరు సెక్షన్ తీసుకుంటే ఎక్కడైనా దట్ సెక్షన్ అనేది ఎక్కడైనా అప్లై చేసుకోవచ్చు. బట్ డబుల్ ఇంటిగ్రేషన్ మెథడ్ లో ఇక్కడ సెక్షన్ తీసుకున్నప్పుడు ఈ సెక్షన్ లోడ్ దాటితే అంటే ఈ సి పాయింట్ దాటితే we cannot apply this section in between B and C. Okay, that's why this double integration method will not use for the multiple loads or మల్టిపుల్ లోడ్స్ కి మనం ఇది యూజ్ చేయలేం. సింగిల్ లోడ్స్ కి అయినా లోడ్ దాటిందంటే ఈ సెక్షన్ మనం అప్లై చేయలేం. ఓకేనా, లెట్ us see what is going on this double integration method for simply supported beam. In this problem, this example 5 తో మనం క్లోజ్ చేద్దాం ఈ క్లాస్ ని. Example 5, what is example 5? Simply supported beam, point load at center. So let us consider X-axis section at a distance of X from the left support. Bending moment at X6. What is the bending moment at X6? If you take the X-axis section here, what is the bending moment? You have to consider all the moments of the forces on the right side. Right side lo unna forces enti ikkada reaction force of RB undi and W is the point load undi. Ee rendu kuda moments develop chestayi X6 about the X6. So ee clockwise movement develop cheste W, RB అనేది యాంటీ క్లాక్ వైజ్ మూమెంట్ డెవలప్ చేస్తుంది. సో మూమెంట్ డెవలప్డ్ బై ద RB is positive, మూమెంట్ డెవలప్డ్ బై ద W is negative. Yes students, are you getting my point? So bending moment at X6 is M. Before going to find the bending moment, you should know the reaction forces RA, RB. So to find the RAB by symmetry directly we can write W is the load acting which is at the center and the same load will be shared by the each support. So half of the load is shared by the support A and the remaining half of the load is shared by the support B. Therefore, out of this W by 2 is the RA, W by 2 is the RB. RB becomes RA, RB are equal and which is equal to W by 2. Otherwise, we can find like this. To find the reactions, RA plus RB equal to W. So RA, RB are the upward forces. Sum of the upward forces must be equal to the sum of the downward forces. So only one force is there, one load is there in the downward direction, W. So RA plus RB equal to W by taking the equilibrium equation, sigma F equal to 0. Okay, next by taking the bending moment at point A, by taking the moment at point A, if we take the moment at point A, sigma MA equal to 0. That is the another equilibrium equation. So moment at point A is RB into L distance, it is in anti-clockwise direction, positive, W into L by 2. Midpoint కాబట్టి ఇది L by 2 distance ఉంటుంది. So RB into L equal to W into L by 2 అవుతుంది. RB into L equal to W into L by 2. So LL cancel, RB equal to W by 2. Therefore RB equal to W by 2. By substitution of RB in this equation, equation 1, we will get the RA value. So RB W by 2 అయినప్పుడు RA కూడా W by 2 అవుతుంది because total load is W. So after getting the reaction forces, we should find the moment M. What is the bending moment at X6? So let us see the bending moment, how to find the bending moment at X6. So RB into ఎంత చేయాలి? RB into L minus X చేస్తాం because X distance లో మనం సెక్షన్ కన్సిడర్ చేస్తున్నాం కాబట్టి మనం సెక్షన్ దగ్గర బెండింగ్ మూమెంట్ క్యాలిక్యులేట్ చేయాలనుకుంటే RB into L minus X వేసుకుంటాం. RB into L minus X A direction lo anti-clockwise direction. So anti-clockwise direction is positive. RB value enta W by 2. So W by 2 into L minus 6 is a positive. Minus ఎందుకు ఇది clockwise మూమెంట్ డెవలప్ చేస్తుంది అందువల్ల మైనస్ W into ఎంత డిస్టెన్స్ చేయాలి ఈ రెండింటి మధ్యలో డిస్టెన్స్ ఎంత how much this distance perpendicular distance we know that the total distance from A to C is L by 2 isn't it half of the length L by 2 this distance is L by 2 this distance is X so L by 2 total distance minus X then we'll get the distance from the load to the section. Okay, students, so I written here W into L by 2 minus X. Minus sign is clockwise movement. So after simplifying this equation, we will get Wx by 2. W by 2 is the WL by 2. Here also minus WL by 2 will cancel. Here minus Wx by 2 minus minus plus Wx. So Wx minus Wx by 2 is Wx by 2. M value is Wx by 2. Bending moment at Xx. Then this by substituting this bending moment equation in the curvature equation, we know that curvature equation is from the curvature equation EI d square y by dx is equal to minus m. It is like fixed for all the problems curvature equation. So upon substitution of m value here, what is m value? M is equal to wx by 2. M is equal to wx by 2. So minus m kabatti minus wx by 2, right? Okay, students. So by integrating this equation, curvature equation, EI d square y by dx square is equal to minus wx by 2 మనం integrate చేసుకుంటాం. By integrating the above equation, we will get first integration. After integrating once, EI dy by dx is equal to, what is the integration of wx by 2 minus w by 2 is the constant, x integration is x square by 2. So 2 into 2, 4 in the denominator minus wx square by 4 plus c1. Then by integrating once again, we will get on the left hand side EI y is equal to minus w x square by 4 integration minus wx cube by 12. So minus w is constant, 4 is the constant, minus w by 4 into x square integration x cube by 3. 3 into 4 is the 12 in the denominator, therefore minus wx cube by 12 plus c1 into x plus c2 is the second integration constant. So these are the two equations to calculate the slope and deflections including constants of integration. Okay. So by substituting the boundary conditions, what are the boundary conditions? From here onwards, the boundary condition is changes. The boundary conditions for the cantilever beam are different than the simply supported beam. So for simply supported beam, the boundary conditions are, first boundary condition, at x is equal to 0. At which point the x is equal to 0? If we say take the section xx at A, at left support, if we take the section at this point, x becomes 0. That means if x is equal to 0, what is 0? The beam is not deflecting at point A, therefore deflection is 0, isn't it? At x is equal to 0, deflection is 0. I written here one of the boundary condition at x is equal to 0, y 0, y is the deflection. Okay, so at the left support, deflection is 0. And another boundary condition for this simply supported beam is we should not take the boundary condition at point B, because the section is applicable up to point C only. Therefore, we should take the boundary condition up to C. So another boundary condition is at x is equal to L by 2. At C, L by 2. That is the midpoint of the beam. That's why we take the boundary condition at x is equal to L by 2. At L by 2, what is the parameter? Which parameter is 0? Either slope or deflection? It is deflection is maximum. Wherever the deflection is maximum, slope is 0. Now itself I explained that if we draw the tangent at this point, it will be horizontal. So the horizontal tangent angle is 0. So slope at the center of the beam, if it is load is acting at the center, the slope is 0. So if x is equal to L by 2, the slope is 0. I written here at x is equal to L by 2, slope dy by dx is 0. At the center, slope is 0. So upon substitution of these two boundary conditions, we will get the constants of integration C1 and C2. So from the boundary condition 1, ఈ కండిషన్ ని మనం ఎందులో సబ్స్టిట్యూట్ చేయాలి? y ఉంది కాబట్టి డిఫ్లెక్షన్ ఈక్వేషన్ లో సబ్స్టిట్యూట్ చేయాలి. Upon substitution of first boundary condition, in place of y 0, left hand side 0, in place of x also 0, these two parameters 0. So C2 only remains in the equation, C2 equal to 0. So we will get the second integration constants first upon substitution of first boundary condition. Then from the second boundary condition, what is the second boundary condition? At x is equal to L by 2, dy by dx is equal to 0. So upon substitution of second boundary condition in the slope equation, because dy by dx is 0, we know the slope, then upon substitution of that boundary condition, so left hand side becomes 0, dy by dx is 0 kabatti left hand side it will be becomes 0. That is equal to minus w by 4 is a constant. In place of x we should substitute L by 2. So L by 2 whole square plus C1 is there. So minus w L square by 16 it will become, the equation becomes w L square by 16, because L by 2 whole square is L square by 4, 4 into 4 16. So minus w L square by 16, therefore C1 is equal to, it is positive avutundi, C1 equal to w L square by 16. This is the C1 value upon substitution of second boundary condition into the slope equation. Okay, these are the two constants of integrations. Okay students, after substitution of these two constants of integrations into required slope and deflection equations, we will get the final slope and deflections. Therefore slope equation is ei dy by dx is equal to, ei dy by dx is equal to this equation, minus wx square by 4 plus c1 place lo wl square by 16. C1 place lo wl square by 16. Similarly, deflection equation is ei y equal to minus wx x cube by 12. This is the deflection equation, minus wx cube by 12 plus c1x ante plus c1 place lo wl square by 16. C1 place lo wl square by 16x plus c2 value is 0. So minus wx cube by 12 plus wl square by 16x, c2 value 0 got it right. These are the slope and deflection equations, final slope and deflection equations after eliminating the C1, C2. Okay, so by using these two equations we can find the slope and deflections at each point of the beam. Ekkadaina manam find chesukochu slope and deflections in the beam lo. So first in this problem, slope at the left support, supports daggara center point daggara slopes find cheyamannadu, and deflection 2. So slope at the left support and the left support daggara x value 0, isn't it? So if you substitute in place of x 0, we will get the slope at left supports. So slope equations lo x place lo 0 substitute cheste manaki slope at a point vachestundi. So ei into dy by dx place lo nan theta a raskuntunnanu. Theta is the dy by dx slope and a is the slope at point a. Ei theta a is equal to, if you substitute in place of x 0, this parameter becomes 0. So remains the value is wl square by 16 is the remaining value. Okay, so ei theta a equal to wl square by 16, therefore theta a is equal to wl square by 16 ei. This is the slope formula at left support. Similarly, the slope at the right support is also equal, because once again see the diagram, the beam bends like this. Whatever the slope developed at the left support, the same amount of slope will be developed at the right support, but it is in anti-clockwise direction, negative slope. Similarly, the same slope will be occurs at the right support. So therefore we can write theta b, slope at the right support theta b is equal to, simply we can write minus theta a. Slope magnitude wise is equal, but direction is negative slope. Therefore minus wl square by 16 ei is the slope at the right support. Negative represents the anti-clockwise slope. Okay, slope at the center means at x is equal to L by 2. So upon substitution of L by 2 in place of X in slope equation, we'll get the slope at point C. So EI theta C, C is the center point. EI theta C is equal to minus W by 4 in place of X, we can substitute L by 2 whole square plus WL square by 16 is constant value. So here minus WL square by 16 plus WL square by 16, it will become 0. So at the center slope is 0. Okay, center lo slope 0 వచ్చింది మనకి. Again we already we substitute the slope, center point slope is 0. We after finding the slope at the center, we'll get the 0 slope. So it is correct. Theta C is 0. These are the slope at each point of the beam. Next, deflection. Similarly, we can find the deflections at each point. X is equal to 0, X is equal to L by 2. So if you substitute in place of X 0, we will get the deflection at point A. So మనం ఇక్కడ substitute చేసామనుకోండి, deflection equation ఇది. దీనిలో X place లో 0 substitute చేస్తే ఈ right hand side parameter 0. So ఈ 0 అయినప్పుడు Y కూడా 0 అవుతుంది. Y is equal to 0 by EI. So 0 by EI is 0. So deflection at the left support 0. Deflection at left support YA is 0. Deflection at the right support is also 0 by symmetry. By symmetry, we can say that deflection is on the right support is also 0. YB is also 0. So deflection at the center. If you want the deflection at the center, you have to substitute L by 2 in place of X in the deflection equation. So deflection equation lo X place lo L by 2 substitute cheyandi. We will get the deflection at the C. So EI YC. YC is the deflection at the center point C. YC రాస్తున్నప్పుడు X place lo substitute చేయాలి, L by 2 substitute చేయాలి. So EI YC equal to minus W by 2L is the deflection equation, final deflection equation. EI YC equal to minus W by 2L in place of X L by 2, L by 2 whole cube. Yeah, written L by 2 whole cube plus WL square by 16 is there. WL square by 16 in place of X again we will write X L by 2. WL square by 16 into L by 2. So minus WL cube by 8 into 12 is the 96 plus WL cube by 16 into 2 32. So 96 is the LCM minus WL cube plus 3WL cube. So 3WL cube minus WL cube is 2WL cube. 2WL cube by 96. WL cube by 48. Therefore, YC is equal to WL cube by 48. Here is the deflection at the center. Deflection at the center, which is also maximum deflection. We can write it as Y max or YC. Y max or YC is the WL cube by 48 is the formula for deflection. Okay, this is the fifth example, I think so. Fifth example. So in the next class, we'll go for remaining problems. Sixth example, seventh example. Seventh example is under Michaelis method. Up to now, sixth example is double integration method. And second method, Michaelis method, we can use for multiple loads like this. Okay. Okay, let us close this class up to this point. Okay, students, bye. Have a nice time.